Okay, welcome back. Sorry about that. I don't know. I lost the internet or something for a second. Like it must have completely cut out because normally I get some kind of warning, but it like immediately shut off the stream. So anyway, hopefully uh, won't have any more issues today. So I don't know what exactly was cut off there because I didn't have time to go back and look at the first part of the lecture. So I'm just going to kind of rehash what I was saying here. So, as I know that at least I got the bit about this being a true average here because I saw the comment about this being surface area. So yes, this is 1 over the surface area of this sphere, so it is like a kind of average of the values of this quantity over the sphere. Of course, this quantity only depends on the initial data, phi and c. So the initial data on the boundary of this ball, on this sphere, is what determines my initial displacement at this point. So I want to ask this question that I asked when I had D'Alembert's formula in the 1D case. I'm at a point here, right, at some time. Now I can't indicate the time axis here, right? I'd need another, it'd be 4D. I'm not going to do that. So at a fixed, my time, or my time here is indicated by some t. So at a fixed position x naught and t, what points contribute to my displacement here, right? I want to know what points contribute to this. Well, from Kirchoff's formula, it is exactly points on this sphere. So I have c is a constant, of course, in my problem. I have some ct amount, right, indicated here. And so I have a sphere having that radius. And that's kind of a terrible drawing that I've made there. Okay, so here, there's my radius ct here. So that this sphere is the boundary of the ball centered at x naught of radius ct. And so what points contribute to my displacement here at the center of this thing? All of the points on this sphere. None of the points inside it, right? Only the points at the sphere, on the sphere. Okay. Notice that this means also that this point itself, right, where I like this point where I want to know my displacement, right, x naught, the entire contribution to displacement here is given by all the points on this sphere, right? That's what Kirchoff's formula tells me. Okay. Now let's ask, so that is the domain of dependence question, right? So remember, this is analogous to the question we asked before in the 1D case. So in the 1D case, I fixed a point here, xt, and asked, what points prior to this contribute to this point, and we found that, it's a region that looks like this, right? Where like here's x minus ct, here's x plus ct. Notice that we still got like a ball of radius ct, but now it actually included like everything here, right? I needed all of these points. And this is not the boundary, right, of this region. This is actually the analogous thing here is actually the ball of radius ct centered at x. Right? So the points we got were the points inside this ball. Here, the points we get are only the points on the boundary. Okay. And so, the idea here is that u of x naught t depends on the initial values, say u of x0 only, so only if x minus x naught is exactly equal to ct. So only if it is on this boundary. Okay. Asking the question about its domain of influence, right? So suppose that I give you initial information, right, about u and its derivatives at a point. The question is, what later points are influenced by values here, right? It turns out it's exactly the same thing. It's exactly the same set. It's this sphere. And so, for the domain of dependence and influence, I have the exact same picture. I'm just saying the kind of the opposite thing here, right? So it's like the exact same picture interpreted in two different ways. To see that in the textbook here, glares are kind of ridiculous here. Okay, there we go. So as it says here, two interpretations of the same figure. Here is a sphere of radius ct centered at x naught. To see that this is the domain of dependence, the value of the disturbance at position x naught in time t depends on the initial disturbance at t equals 0 on the sphere of radius ct. To see that this is also, this exact same picture is the domain of influence, an initial disturbance, that's at t equals 0, at the position x naught will influence the value of u, the displacement, at time t on all points which lie on the sphere of radius ct. Okay, if I were to draw the same sort of picture. So the thing is here, you might say, wait, you cheated because the picture you drew here is different. And I admit it is. It is different. In fact, what is going on in the 1D case is the same from one point of view, because what is actually needed from D'Alembert's formula, right? What values do I need? I need values of the initial displacement at the boundary of this interval, right? Just these points. So the boundary of a 1D thing is just these points. But I still need to integrate over this region that initial velocity. So, okay, you know, what exactly does that mean? Can I still break this down into just needing boundary points? We'll talk a little bit more about that in a second. But the main reason this picture is different is because this was my spatial variable, and actually this other axis was my time variable, right? So this is kind of a different thing that I've drawn here. This picture is different than what I'm trying to say here. So here I have only my spatial variables showing up, right? X, Y, and Z. So if I tried to draw like a 4D picture involving a time axis, what sort of picture would I get out of looking at domain of dependence, domain of influence? If I included the t, this would lead me to the notion of a light cone. You can have a look at that if you haven't seen this notion before. You can look up light cone and what is meant by this. You may have already kind of guessed that something like this would basically be what it is that's happening. From the 1D case, it doesn't look like a cone here, but it's like looks like a, this is like a 2D cross section of a cone. These pictures of domain and dependence and influence we drew for just our typical wave equation on an infinite string in the 1D case. Right? This basically was our one spatial dimension version of light cone, which was just these two-dimensional regions. But this is basically what it is that's going on. So what is the kind of like the main thing here, right? What is kind of the main point? Of causality from Kirchoff's formula. Well, what we see is something called Huygens principle. Which is what? The principle actually says something a little bit different, but one consequence of it, I should say, is that disturbances in 3D propagate on sharp fronts. Okay. So what occurs here that is distinct from the 1D, and we're going to see the 2D case as well. So this is in contrast with the 1D, and we'll see, we haven't actually done 2D yet, right? 2D cases. So what do I mean this propagates on sharp fronts? So let's ask ourselves a question. So in 1D, if a bomb detonates, so if a bomb detonates at, say, position x0 at time t equals 0. Okay. What happens if we are at position, say, x1, then we would feel the disturbance at time, well, when would we? Well, basically, it takes some travel time based on the speed, right? It depends on how far we are from x0. So how far are we from x0? Well, we're the distance between x0 and x1. If we divide that by c, the speed, then this is exactly the time that we would feel that disturbance. But remember in the 1D case, those pictures of the domain of dependence and influence, right? What happens, right? What happens once I feel this disturbance? Well, it turns out that I would continue to hear it, right? I would continue to feel it at all future times past this time. And also, I would continue to hear it at all times t greater than or equal to t1. Right? That was how 1D propagation worked. Right? Go back to those profiles that we plotted. Right? Go back to those profiles we plotted. Go back to those pictures of the domain of dependence and influence. And what this means is that a similar thing is true in 2D. As we'll see. And so we are, if we lived in a 1D or 2D universe, then sound and speech and these things would be it'd be pretty chaotic, because basically once you heard a sound, you would just hear it forever. You just hear it for all future times in this same way. Which is, you would hear some versions of that sound, right? Someone speaks, and then you would hear some version of that sound forever, and that would be how, how you heard things, how you experienced propagations of disturbances like this. So that'd be probably fairly annoying. Um, but this is different in the 3D case, because in the 3D case, these things propagate on sharp fronts. So, for instance, what does this mean? Like, what is the difference here in the 3D case if we were to look at like a cross section of what happens? Right. The idea is that there's an initial disturbance at x naught, and if I'm looking again at a two-dimensional cross section, this disturbance propagating on sharp fronts means that it moves outward from x naught, right, on these sharp fronts. And if you are at position, say, here, right, if this is x1, then once this has, if this is, we'll call this distance here ct1, right? So again, this is when the disturbance reaches you. But once that disturbance passes you, that's it. Right? So once that disturbance, once that sharp front passes your position, then you no longer feel it, right? So you feel it exactly at this point and no longer. Now, Huygens principle doesn't actually say exactly this. One of the things it says is that every single point of a wave front can be considered as the source, right, of other wave fronts, basically. So at each point here, this is now, so the wave front here is a disturbance at this point, we'll call it x2, so that this point now forms the center of another wave front from which these disturbances can emanate. That's actually what Huygens principle says. So So Huygens principle, what does it say? Every point of a wavefront may be considered as the source of secondary wavelets that spread out in all directions spread out in all directions with a speed equal to the speed of propagation of the waves. Now, reading this can be a little bit confusing because it actually seems like this is contradictory with what we said here about this propagating on sharp fronts. And oh, if I'm at this position, once this front passes me, right, that's it, right? Like I don't continue to hear it, I don't continue to feel it or whatever. It's gone. It is past me. But this says that every point of a wavefront is considered as a source of secondary wavelets, right? Secondary like disturbances emanating from that point also in sharp fronts. So then, for instance, like this point here is a disturbance, this point is another disturbance heading out in all directions. And so this statement here, right, about every point being source of secondary emanations here, right? How can that be kind of reconciled with these disturbances propagating on sharp fronts? Well, so here's the question, right? Won't some of the new train of waves, these wavelets, from the advanced wavefront come back to us at some later time, since it says that this spreads out in all directions, right? So, for instance, once this wavefront passes us, won't, for instance, now if Huygens principle tells me that, say, at this point, I can consider that as like source for disturbance that is now heading out in all directions, so it's coming back toward me here, right? The question is like, wouldn't some of these wavelets come back toward me and I hear them again, right? And the answer is yes, they would come back to you at some other time, but because this is happening not just at this point or not just at some of these points I've labeled, but it's happening at every point in all directions, they come back from all directions in such a way that they cancel each other out. And so this thing that I've circled, that these propagate on sharp fronts, that still holds true, right? Now, if you want to look into how this works, it's very interesting. You can do so, but this is kind of the key, and we can read all of this from Kirchoff's formula, so that's nice. Okay. Now the textbook spends a couple of sections deriving Kirchoff's formula, which I'm not going to do at all. I'm mostly just interested in those specific consequences. So what I will do instead is I'm going to hold on one second. Okay, sorry about that. They had to come in and change the filter in my apartment. Okay, so so what was I saying? Yeah. That's the main thing I had going on with Kirchhoff's formula is I just wanted to talk about these consequences from it and see how it relates to what's called the method of descent. I'm not going to go into too much detail about that, but this leads to a similar type of formula in the 2D case, and I just wanted to see the contrast between all of these things mostly. I'm not going to get lost in the weeds of trying to actually derive all these things fully. It would just take too long. Okay, so down to 2D. So the 2D wave equation. And what does this look like? Well, it looks a lot like the 3D wave equation if I don't actually write out that the Laplacian is the 2D Laplacian. All right, so what does this look like? This is u sub tt is c squared Laplacian u, where x now is some, well, I'll write it as some ordered pair x1, x2, and r2, and t is greater than 0. We have initial data as before. All right, so there it is, phi of x, c of x. Again, both of these on R2. Okay, so this is the 2D wave equation. What is the, if we thought of the 3D wave, I mean, okay, the interpretation is always the same. Basically, there's a disturbance in the amount of spatial dimensions mentioned, right? So in 3D, you can think of this disturbance, right, as like signal, right? A signal emanating like in 3 space. For 2D though, for 2 spatial dimensions, you can think about this as the vibration of like a flat membrane, right? So think of some flat like stretched membrane. For instance, the the top of a drum, right? The vibration of the top of a drum is one thing modeled by this sort of thing. So the vibrations in circular drum prescribing boundary conditions here, because this would be a finite thing, of course, the way that we have it here. This would be an ideal membrane, right, that stretches on infinitely in all directions. And so on. You get the point here. So, why did I do 3D first? Here's exactly the reason, right? So question, of course, does there exist a D'Alembert / Kirchoff formula for 2D? The answer is yes, via Kirchoff's formula and the method of descent. I'm not going to go into this in too much detail, but basically Kirchoff's formula can be used, and the method of descent is the following. Basically, we assume we have a solution to the 2D equation. Okay, that solution, of course, looks like a u of x1, x2t. Okay, then the idea is that if we artificially lift this solution to a 3D wave equation, we can do so by basically saying let u of x1, x2, x3t be equal to this thing. So there is no actual dependence on this third variable, right? This thing is actually independent of that variable. Well, this lifts it to a 3D solution, but then we use Kirchoff's formula for this 3D solution. But Kirchoff's formula only depends on the sphere, which is two-dimensional, so you can parameterize the sphere via two parameters that we have present in the solution that we seek, and then we can project this 3D solution from Kirchoff's formula back to 2D. Okay. And what we get when we do that is the following. That if this u of x1, x2t solves this equation I'll call star, then u of xt is 2 over 4 pi ct times the double integral over the two-dimensional ball. So b sub 2d, it's the two-dimensional ball centered at x of radius ct of phi of y plus, I'm parameterizing with y here, so that's my dummy variable, plus nabla phi of y dotted with y minus x plus t c of y divided by the square root of c squared t squared minus y minus x, or the distance between y and x squared, d y1 dy2. So again, we're not going to worry ourselves too much with the specific form this takes. Of course, you can, that derivation that I just did is actually not so bad, and you see what I mean when I say projecting it from 3D to 2D here. That's deriving Kirchoff's formula is harder than taking Kirchoff's formula and using this method of descent to solve this thing. But don't worry about that too much. What I'm really going to focus on here is now this integral is a little bit different. Right? This is a little bit different. This is now a double integral. This is a double integral over a two-dimensional ball So here's x, right? And here, if its radius is ct, then the ball we're integrating over is this thing. So it's this whole region here. Okay. And so how is causality here? So the easiest way to see this is that if we considered, go back to our 3D case, and I talked about how the domain of dependence and influence, if we implemented like the t-axis, uh, this would be a light cone. But when I say it's a light cone, I mean it's not the stuff that's inside. When you think of a cone or a double cone, it's not the stuff that's inside the cone, it's the surface of the cone, right? That's what the picture would look like. Here, though, if we were to draw the light cone, then it's not just the surface of the cone, it's all of the interior points as well. So it's like a solid cone. Okay. So again, the way that this works is that this Huygens principle is false in 2D. Okay, disturbances do not propagate on sharp fronts. At any given position, one feels disturbance at all later times, just like in the 1D case. So, as in the 1D case, Huygens principle is false. And so living in a 1 or 2 spatial dimension universe would be pretty weird for a number of reasons, but this is one particular reason that it would be pretty weird. Okay. All right. Now, we could discuss the wave equation in even larger dimensions, and in fact, right, discussing like general wave equation in or x and Rn, you can even write out solutions in the form that we have for Kirchoff's formula. Um, like in general, like this can be done. If you want to look at the very beginning of this course, I mentioned a graduate text, Evans, on PDE. So this is done in Evans if you really wanted to have a look at it. But we've basically illustrated all the things that we were curious about here. In especially, we spent so much time on the 1D case because it was the thing that was the easiest to handle. And it was the thing where we could kind of get the most intuition. All the pictures were kind of the easiest to draw, and so on. But again, kind of what unifies all the stuff we've done with wave equations together with what we did with first order PDEs is the fact that we have this finite propagation speed business going on. So that the behavior, even when the behavior was slightly different, say for instance in 3D, the causality worked a little bit differently than it did in 1D and 2D, still all of these quantities we were writing down, we could talk about in a way that was, kind of reminiscent of what we were talking about for first order PDEs. But that we're not going to be able to do that with what we do going forward. And so basically, what we want to do going forward is something completely different, right? And it will be unified again near the end. We're going to apply one method to all of the big three. But now, for something completely different. How are we going to progress through the rest of the text? So we will lightly touch, very, very, very lightly touch on chapters 5 and 6. It turns out we don't need a whole lot of them. Okay, that's the main thing to say. So we will very, very lightly touch on chapters 5 and 6. Chapter 5 covers what are called distributions. The main point to get out of this is that sometimes it is very helpful to have a notion of a function that is a little bit more flexible than an actual function. Because as it turns out, actual functions can be a little bit too much to ask the quantity in question to be an actual function. You might think that's ridiculous. You might think kind of a function is the basic object here, so if something's worse than a function, I don't even want to talk about it. But unfortunately, we need some things that are a little bit more wiggly sometimes. You'll see that these things are not so bad. We're not going to touch too much on them, just enough so that what I write later makes sense. Chapter 6, we're barely going to touch on. I'm basically going to define it and just mention it because it will make it, there will be a little bit more of a payoff if you at least are familiar with the form this thing takes later. These are Fourier transforms. Now, we are going to do what are called Fourier series later in the course when we do separation of variables. And I will talk briefly about the relationship between Fourier series and the Fourier transform. Fourier transform, I can't possibly tell you how important it is. It's like one of the most important things ever. And so it's covered nicely in this chapter. We are just barely going to mention it. I will define it and I will say a few things about it. In fact, in 246 you've already encountered something that's very similar in spirit to it, which is the Laplace transform. But the Fourier transform is ubiquitous in so many fields it can't possibly be overstated. So what is the point of even lightly touching on these things? We need both of these to make sensible statements about what we're really interested in, which is what comes next. So chapter 7 is the heat equation, and chapter 8 is Laplace's equation. Now, it's going to be a little weird when we do these chapters first because I'm going to be showing kind of a lot of properties that solutions to these things have without doing a lot of solving necessarily, although there will still be some of that. There will be solution formulas written out and things like that, but mostly we're going to be talking about properties of solutions to these things. And ultimately, what we're going to do after this, we're going to skip chapter 9. So we're skipping chapter 9. And then we will be heading on to really what we're interested in, which is Fourier series. Chapter 10, I should say, we're not going to cover that much either. So you can throw it in the skipped category. We'll just touch on what we need from any of these. Chapter 9, we won't need much at all. So then we're going to do Fourier series, which is chapter 11. And chapter 12 is separation of variables. Which is the method by which we will return to all of these, including the wave equation, and write out some of these. Remember, we looked at the wave equation in the 1D case and when it had two fixed ends, convinced ourselves this was like pretty, this was a pretty complicated situation to be in. And then we asked ourselves, like, well, what do we do in this complicated situation? How do I deal with this? I wrote out a solution in that case, and if you noticed, right, when I wrote it out, it was a separated solution. The x and the t were separated in the sense that I could write my solution as a product of a function of x and a function of t. And that's not a coincidence. The reason why that solution worked out so nicely, or the reason it was separated, is because the method by which we're typically going to deal with those things is going to be separation of variables, and we'll see all of that. Now, In a typical PDE course, as PDE courses were taught for a long time, separation of variables was almost all you did the entire semester. But I think that's a little, I think it sells you short. I think you get a lot more out of a PDE course kind of designed in this way because you get to see a lot more of the flavor of PDE stuff when it's presented in this way. Separation of variables is this mechanical algorithm that if you can, if you can handle the kind of viewpoint that we're taking with all of this stuff, separation of variables algorithm is a fairly easy thing. Once you get the process down, it's a thing that is mechanical, computational. It's fun to do. It's a lot of fun to do them, but it's not something. Once you understand kind of how it works, that's pretty much it. You're good to go. Okay. All right, and so next we begin our quick treatment of what we need from chapters 5 and 6 in order to sensibly discuss chapter 7. So this is the plan. Okay. And so I will do that in the next lecture. So I think this is a good stopping point for us. So this lecture will be uploaded in 2 parts because of me losing internet connection. Sorry about that. I'll label the parts. I've already labeled the second part. I'll go back and label the first part as a part 1. And then I'm going to fold all these into a playlist so that it'll be convenient for you to have a look at later. Anyway, though, that's the lecture here. I'm going to actually record tomorrow's lecture later this afternoon. So I'll let you know when that's recorded, and I'll go ahead and post it. You can watch it whenever you like. And then tomorrow morning, or maybe super late tonight, I will upload the midterm that I mentioned earlier in the week. So your first midterm will be uploaded, and it will cover basically everything that we've done in chapters 1 through 4. Okay, so it'll be very much in the same spirit as the homework, so you can just view it as an alternative homework assignment. It might include, I mentioned like a single chapter 4 problem of some type that you can handle. So anyway, that's that. I will see you all soon.